so your title is Principle of Induction, and we're going to look at the divisibility cases in this instance here. So Principle of Induction. So, from yesterday, do we understand the Principle of Induction? Okay, so Tristan, could you explain to me what the Principle of Induction is? So there are three cases you need to prove, and if you prove those three cases, you proved it for all values.
So base case.
Base case.
Base case, then n equals k, then n equals k plus 1.
Yeah.
And along the way, both sides should equal each other. So
Yeah.
Yeah, except for some cases where the base case can't actually apply to the equation.
Yeah, perfect. So for a lot of proofs, a lot of proofs are written as equations. You prove that they are equal. But the point being that there are so many values that you need to prove, right? So if I said to you, is this true for every value? Can you check it's true for every value? It's not feasible, right? So you actually only need to check three. So Josh, the idea is, you know how the process of climbing a ladder works? So you know how a ladder works, right? There's rungs on a ladder. So if you're on the principle is, if you are on if you're in the middle of a ladder somewhere, can you get to the next rung of the ladder? That's the idea. So then, do you agree the only thing you need then to climb the ladder is to be able to take the first step? So if you get to the first step, because you know how to get to the next one, you can get to 2. Because you know how to get to the next one, you get to 3, and so on. So, you prove, for inductive proofs, you prove the base case. So the base case may not always be 1, but it will usually be 1. And then you prove n is k, and then you prove n is k plus 1. So these two work as a pair. So the idea is, Joshua, that if you prove it's true for some general k, and then you prove it for the one above that, these two work together. So the idea is, if it's true for some value, it's true for the one above it. So then, do you agree by solving 1, how does that show it's true for all of them? So if it's true for 1, it must be true for 2. And if it's true for 2, it must be true for 3. And if it's true for 3, it must be true for 4. So these two work together, essentially. So by proving these three cases, you then proved something by induction. Right, so I'm going to do the 2 homework questions I set you from yesterday. So just not really homework, but like passive homework. So we've used these 2 expressions before. So the sum of the first r squared number of the first square integers is 1 over 6 and m plus 1 to m plus 1. So I'm going to use induction and I'm going to prove this. So you need to know it for sums, you need to know it for matrices, and you need to know it for divisibility. So we did sums and matrices yesterday, we're going to do divisibility today. So I will quickly use these to recap sums, and then I'll also recap matrices. That's fine. Right, so this statement is true for all n in the natural numbers. So again, I'll reiterate what I said yesterday. What's the base case of the natural numbers? What's the smallest value in the natural numbers? 1. So, to a reminder, the natural numbers are positions, essentially. Is there a 0th position? No. The first position when you run a race is 1, then 2, then 3, and so on. So the base case is at n equals 1. So we just test this is true for n is 1, first of all. So the left-hand side would be the sum from 1 to 1 of r squared. So do we agree it's 1 squared, which is just 1. And then the right-hand side is going to be 1/6 times 1 times 2 times 2 times 1, so 3. So do we agree this is 6 divided by 6, which is 1? So do we agree left-hand side and right-hand side are equal? So base case is true. Base case is correct, yeah. So next case we do is n equals k. So the statement we're trying to prove is that instead of k values, it's the first, instead of n values, sorry, it's k values. So from 1 to k of r squared equals, and then instead of n, it would be k, so 1/6 k plus 1, 2k plus 1. So this is always true by inductive hypothesis. So the idea of induction is you have a hypothesis, you're given a statement, and you use induction to test that it's true. This is my hypothesis, so what we do for this step here, I've just applied the n is k, so it's just this here. So we don't know this is true, but we say it's true by our hypothesis. So our hypothesis says this is true. So the last one then, if I go over here, and let me just check that I am in frame here. Yeah, we should be good. So the n k equals k plus 1th case, so it's true for 1, It's true for k, and now we need to show it's true for k plus 1, and then we're good. So the statement is this, so do we agree with just replacing n with k plus 1? Yes? So this is the statement that you need to prove. You need to prove that k plus 1 to 1 of r squared, and it's equal to 1/6. Going to be k plus 1, k plus 2, and then this bit here, so 2 times k plus 1 plus 1, so it's going to be 2k plus 3. So we need to show that this left-hand side is equal to this to prove the k plus 1th case. So I imagine you'll notice, have we actually done anything really difficult so far? We did the 1 case, which is easy, and we did the n case where we literally just said, trust me, it's true. So we haven't actually done any work yet. So this bit here is where the actual work is. So let's go through it. So we need to start here. Any kind of proof question is you start on this side, you have to get to this side. So allow me to change pens, so sometimes the camera can see a bit better. So the sum ones are always the same. So you always start with the sum of k plus 1 terms. So what I'm going to do is I'm going to write this as the sum of k terms, r squared, plus k plus 1 squared. So allow me to elaborate on what I'm doing here. So you can, the sum just means this expression evaluated at 1, and then evaluated at 2, then 3, then 4, then 5, then blah blah blah, then k plus 1, and you add them together. So what I can do is this would be the same as the sum up to k plus this evaluated at k. Is that okay? Does that make sense? So the point being that I get this. So this is the whole goal. I'm trying to get this in here because I know what this is equal to. It's equal to this from my k part. So, do you see how with any sum inductive proof, it would always be this. You just split it as k and k plus 1. It's always the same thing. So from this, from my inductive hypothesis, I know that this is 1/6, k plus 1, 2k plus 1, and then I know it's plus k plus 1 squared. So all I've done is replace this with this down here. So now the equation is a case of rearranging, and what's the end goal? What am I going to try and get to? This right hand side here. So if I do that, I prove the case. So I'm going to first of all make this 6 out of 6, so I can keep this 6 on the outside, because this has a 6 on the outside, you can see it's going to be. Right, so what do these two brackets have in common? K plus 1 and 1/6, yeah? So I'm going to take out k plus 1, and I'm going to take out 6. So then it's going to be k, 2k plus 1, and then over here it's going to be 6 times k plus 1, yeah? All happy with that? So then it's 1/6 k plus 1, and then expanding this, I'll do it down here so I'm on the right again. So it's 2k squared plus k plus 6k plus 6, yeah? So do we agree this bracket here would be 2k squared plus 7k plus 6? So do we agree we've got to factorize this now, right? Yeah. So even if you're not great at factorizing it, you kind of already know what it's going to be. Yeah, very much so. So I'll do this over here. So this would be equal to 1/6 k plus 1, 2k plus 3, and k plus 2. So have I started here and got to here? Have I started there and got to there? I started here, all the way down here and here. So is the k plus 1th case true? Yes, it is. So then at the end, you conclude true for n equals 1, k plus 1. So true for all n in natural numbers. That's how you conclude that, essentially. Yeah?
What's that sign before that?
That means for any. It's like an angle, so it's like that. It means for any. And then there's also another symbol with a backwards e. That means this there exists, but you won't see that one. So that just means for any. I'm lazy. I don't want to write 2 words. So I'll write 3 lines. Right. So the other one I said I was going to prove was this one here. So the sum of the cube numbers equaling 1/4 n squared n plus 1 squared. So do you remember this was also one of the ones I mentioned to you? We're going to prove this by the same principle. This one is actually easier. I would say this one is actually much easier. Actually, I don't think you have to factorize a quadratic. Yeah, Do you see how this quadratic here is just n and then n plus 1? So actually no, the quadratic you'll get won't have a coefficient on the n squared, I believe. Right, so base case first of all. So this is true for all n in the natural numbers. So what's my base case in this case, because it's the natural numbers? Do we agree it's 1? So for n equals 1, this will be the sum from 1 to r equals 1 of r cubed. So this will be equal to 1 cubed, which is 1 on the left-hand side. This is left-hand side. And then on the right-hand side, I'll move to the side so the camera can see. So on the right-hand side, it's going to be 1 over 4 times 1 squared plus 2 squared. So do you agree this is 4 divided by 4? So 1. So the n plus 1th case is true. And then n equals k is our inductive step, essentially. Actually, I can't remember the inductive steps, the one after. I don't remember the technical name for it. But so for this one here, this is from the sum to k of k numbers, of k cubed numbers. And by our inductive hypothesis, it's equal to 1 over 4 k squared, k plus 1 squared. So just trust me, this is correct. You just say true by inductive hypothesis. So by the hypothesis I've just made up, I think this relationship is true. So by my relationship, when I do it with k numbers, it should be this. So just trust me, that's what it is. And then n equals k plus 1. So again, all the work is in this k plus 1 case. Getting to this point, you agree, is essentially just formality. It's literally just set up. So we start here. So with k plus 1 numbers. So we replace n with k plus 1. R cubed. Right, so the goal, and again, I want to emphasize this, as I mentioned it yesterday, you should set what the goal is that you are trying to get to. So my theorem says that it should be this. That's what my hypothesis says. So I've got to get from this side to this side. Right, so we start here, and I go from here. So R cubed. So do we agree I can split this as the sum of k numbers, or sum of k cubed numbers, and then this evaluated at k plus 1. So that statement there is correct. So it's the sum of up to k plus it evaluated at k plus 1. So now, the whole point was to get this term to appear. So now this term has appeared, what can I do? Use my n equals k step. So what do I know this equals? This bit here, according to my hypothesis anyway. So this is equal to 1 over 4 k squared, k plus 1 squared, and then plus k plus 1 cubed. And as I promised you, this one is going to be really easy. So do we agree we want to get this over 4 on this one as well? So we're going to write 4 and then over 4. Right, so anybody tell me what am I taking out of all of it? K plus 1 squared I can take out, right? So 1 over 4 k plus 1 squared, and then what's left is k squared, and we agree 4 times k plus 1. So 4k plus 4 really, and we're not going to stretch that out, no need to. So then the last bit here, so this is 1 over 4 k plus 1 squared, and what is that factorised to, I wonder? Yeah, factorises to that. So is my k plus 1th case correct? Yes, it is. So then you would conclude that true for n equals 1, k plus 1. So true for n in the natural numbers. Okay, so take a sec. Has anyone got any questions before we move on? So we're going to do a matrix one next. So again, just recapping what we did yesterday. And there is a worksheet on this so you can have a go at. So does anyone have any questions on this at all? So a part of this I haven't really spoken about is the hypothesizing itself. So on our spec, you don't actually have to create these hypotheses yourselves. On the Excel spec, it expects them to actually state the hypothesis themselves, which I think is absolutely insane. But they're not terribly difficult to work out, if I'm honest. So I should have an example here if I just make some space really quickly. So, Tristan, could you remind me what the example we did yesterday was for the matrix one, just so I can show it on the video?
For induction math, 1, 1, 0, 2. So 1 at the top.
Matrix A is 1, 1, and then 0, 2.
Yeah.
So matrix A is 1, 1, 0, 2, and what's the hypothesis? A to the power of n.
And is 1, then 2n minus 1 at the top. And at the bottom, 0, and 2n.
2 to the n, okay. Right, so this is a typical matrix one, so like I said, you need to know how to do this for series, for matrices, and divisibility. Divisibility is probably the hardest one, but in a way it's also the easiest, depending on how you find it, again, and then the theory aspect. So, let's do the base case first of all. So, for any n in natural numbers, so what will our base case be here? N is 1, right? So, the statement here is this, so left-hand side, I'll do it over here just so we've got space. So the left-hand side is equal to a to the power of 1, which is 1, 1, 0, 2, which is just that. And then the right-hand side is this matrix here, and we evaluate it at 1, 2 to the 1 minus 1, 0, 2 to the 1, which is 1, 1, 0, 2. So does the left-hand side equal the right-hand side? Very much so. So for our n equals 1 case, that is true. And now we go to our n equals k case. So by our inductive hypothesis, a to the k is equal to 1, 2 to the k minus 1, 0, 2 to the k. So, and this is true by inductive hypothesis. And then we move on to the obviously where all the work is, so n equals k plus 1. So we want to show, and again, write the statement you need to show. A to the power of k plus 1 is equal to 1, 2 to the k plus 1, minus 1, 0, 2 to the k plus 1. So this is the statement we are trying to prove. So do we agree we're going to start here and try and get to this to prove it? So I'm going to do it over here because there seems to be a bit of space. So a to the k plus 1, do we agree that that is a to the k, so I'll write the matrix actually, I'll write it formally. Do we agree that this is 1, 1, 0, 2 to the power of k plus 1? Yes? All happy with that? By the powers of indices, this is 1, 1, 0, 2 to the power of k times by 1, 1, 0, 2. So again, be careful because matrices aren't commutative, so the plus 1, the extra 1 has to come out on the right. So just happy with your indices, those right, happy with why I can do that, why I split this. Okay, so going back to what I did with the series, the whole idea was I made the n equals k step appear down here. So have I done that here? Have I made this step here appear? Do we agree that this to the power of k is this? So writing this matrix here is actually equal to this. So it's going to be 1, 2 to the k minus 1, 0, 2 to the k times by 1, 1, 0, 2. And at this point, do we agree it's a matrix multiplication? And what should it come out to be? That, if it's true. If it's true. So I may have to make some space here before I do this, because again, I don't want to cram too much in the corners because of the video. I want the quality to be like at least watchable. So if I just give myself some space up here, and I'll finish this one off, and then we can look at a divisibility one. Okay, so finishing this off, we perform this matrix multiplication like so. So it's 1 times 1 and 2 to the k minus 1 times 0, so it's just 1. And then it's this row here times this row, so it's 1 times 1, and then 2 times k minus 1. That minus 1 should be there, it's not a power. Right, so it's 1, so it's going to be 1 plus 2 times 2 to the k minus 1. And then we go to the lower row, so it's 0 and 2 to the k times 1 and 0, so 0 times 1 and 0 times 2 to the k, so do we agree it's 0? Yep. And then for this bottom right one, so 0 times 1 and 2 to the k times 2. So 0 times 1 is 0, and 2 to the k times 2. Okay, almost done. So 1, 0. So do we agree here? And I'm going to do it as a subpart. So 1 plus 2 times 2 to the k minus 2. So do we agree that's 2 to the 2k minus 1? Yeah? What is 2 times 2 to the k? What's the power? 2 to the k plus 1. Yeah, it's another 2 times 1. So essentially this is going to be 2 to the k plus 1 minus 1. And what about this one here? What did I just say 2 times 2 to the k is? Yeah, 2 to the k plus 1. So my step is correct here. So this is indeed correct. So my k plus 1 step is correct. Let me take this as well. So therefore true for n equals 1, k plus 1. So true for all n in the natural numbers. Okay, I'm going to show you a divisibility one. So divisibility, yeah.
Do we ever actually get a question to see that proved by induction that this doesn't equal on the inside? We'll have to go through it and find out why it doesn't.
I'll just say no, because there are ones like the ones I showed you where the base case doesn't work. But do you remember in that one specifically, it was stated weirdly? So if I remember rightly, they said, show that if n equals k is true, show that n equals k plus 1 works. So in the question, they don't say by induction, they say, if n is k is true, show that n equals k plus 1 is true. But then the part B was, look, you show that the base case doesn't work. So if I'm going to say no, I'm going to say no to your answer to your question, no, I don't think it would. The induction is used to prove things, it's not used to disprove things. So there is something else that we do that's called counterexample, but we do that in year 13.
Yeah.
Look.
You know how you said sometimes so the base is going to be n is greater than equal to 2?
Yes.
It's something you're going to be a natural number.
No, so allow me to, okay. So what I can do, I'll do this one here. So I'll go back to the cube when we did, and I'll kind of make a point of this. So specifically, if the domain, for example, is different, you need to examine the domain and just check for what values it's actually asking you to prove it for. And I'll show you what I mean. So the one we did yesterday, oh sorry, the one I did just now, was this one here, right? So sum of n, so r equals 1, r cubed is equal to 1 over 4. N squared, n plus 1 squared for n in the natural numbers, right? That's what I said, yeah? So, if it didn't say this, if it said n greater than or equal to 2, n in the natural numbers, do we agree it's the natural numbers still? Or what's my base case? What's the first number it's actually defining for? 2, so your base case is 2. That's the only distinction. Thing is, we just proved this is true for all natural numbers, so all this will be is instead of it equaling what it being 1 is 1, you'll get 8 equals 8. That's the only difference. That's literally all. Oh no, in this case, it'll be 9 equals 9, but you get the idea. It'll literally be the same thing. They'll be equal. You just start at a different value as well. So I'll do it here quickly if you want. So you would start this exactly like you would normally, but your base case would be 2 because the base is the lowest number that it's the asking you to prove. So left hand side would be sum of 2, r equals 1, r cubed. So do we agree this is 1 cubed plus 2 cubed? Yeah. So this is 9. And then on this side here it's equal to 1/4 of, so it's, we just n is 2, right? So 2 squared times by 3 squared. So it's 1/4 of 4 times 9, so 1/4 of 36, which is 9. So therefore, left hand side equals right hand. And then do you agree it's identical as to what it was before? Then the base case is the only thing that's different. That's the only slight change it would be. Right, so let's go through the divisibility one then. So I'll be honest, the ones you get for this are generally quite nice. They can get a bit out of hand. They can. So we're going to do some that get a bit out of hand a bit later on. But for now, we are just going to do the simple ones. So, first of all, we need to define how you write an odd and even number algebraically, or how you define a multiple of a number algebraically. So, if I said to you, prove to me, Yashin, that 25 is a multiple of 5, prove it to me, what would you do?
Let's do 5 like this.
Yeah, absolutely spot on, issue, yeah. So, my point being, what does it mean to be a multiple of 5? What's the definition of a multiple, specifically? If I said to you something's a multiple of 5, what group of numbers is it in? Is in a multiples of times table, right? It's in it's in the 5 times table. So, if and again, I need to change this rag because it just, all it does is put ink back on the board. So, if I said to you, prove that a number, say if I said to you, show me 25 is a multiple of 5, I would say to you, it can be written as 5 times 5. So the idea is it can be written as 5 times some number, right? So if I said to you that k is a multiple of 7, how would you write that algebraically?
7k.
Not quite. So it means that k can be written as 7 times some number, where r is a natural number. So do we agree if I said that 11 is a multiple of 2, because I can write it as 2 times 5.5, is that really a multiple? No, it has to be a whole number as times by, right? So specifically, if k can be written as 7 times some number, where r is a natural number, this is the definition of it being a multiple. Yeah. So if I said to you, if it's odd, if it's even, do we agree? If I had to show you k is even, do you agree k can be written as 2 times r? Where r is a natural. It means it can be written as 2 times some whole number. Okay, so the proof you're going to get is relatively simple. So you're familiar with the principles of induction now. So the idea is, do your base case, you do your inductive step, your n equals k, and then in the n equals k plus 1 case, you make the k case appear and use it. Right, so show that 5 to the power of 2n minus 1 is always divisible by 24. Oh, sorry, it's divisible by 24. So show that whatever n you use for any n in the natural numbers. So this is the question. Show that 5 to the power of 2n minus 1 is divisible by 24 for any n in the natural numbers that you put in there. So, what's my base case? 1. So, first of all, let's actually write, so we don't actually have an equality statement here. There's not actually an equality, right? So when it says 5 to the 2n minus 1 is divisible by 24, what should I be writing? 5 to the 2n minus 1 is equal to what? 24r, where r is a natural number. So that's the statement we're being asked to prove, yes? Is that okay? So, left-hand side. So, and then again, so base case being, hang on, so I should be 4 here. So let's skip steps. So, for n equaling 1, we're happy why n is the base case, why 1 is the base case here, first natural number. So do we agree left-hand side is going to be 5 to the power of 2 times 1 minus 1. So do we agree is 24? And then 24 is in the, so is that equal to 24? Is that in the 24 times table? So there's not even any left-hand side, right-hand side here really, it's just showed that it's in the 24 times. If you had something a bit more complicated, you would have to divide it by 24 and show it. But do we all agree this is very clearly in the 24 times table? Okay, and then in the n equals k case, 5 to the 2k minus 1 equals r. And then we call it r hat because we agree it would be a different r to appear. So we call it r hat for r in natural numbers. So for r hat in natural numbers.
So 24 r hat.
So it's just equal to 24. In this case, r is 1. So r is just a
No,
24.
Oh, sorry, 24 r. Yes, you're absolutely right. Yes, 24 r. Okay, for r in the natural numbers. So n equals k plus 1 case. Right, so do we agree that this would be 5 times 2 to the power of k, 2 times k plus 1, or in the power of 5, and then minus 1, and equaling 24 r hat. Again, different r's. You could use different letters, you could use s, t, and u, or whatever you want to use really. I was using r's here, but you can use whatever. So we need to show that this here this statement here is divisible by 24. Yes? Right, so as with the same principle as always, do you agree we start with this side and get to this side? Let's do it then. So 5 to the power of 2 times k plus 1 minus 1. I put it to you, this is 5 to the power of 2k plus 2. Yeah? Is that alright?
Oh, yeah.
Yeah. So, I want you to, this is why I did this last, because you have to, again, you have to get that idea that you're looking to make this. What's the power on this one here? Power of 2k, right? So do we agree I want to write this as 5 squared, 5 to the power of 2k minus 1? Yeah, so now do you agree I've created the 5 to the 2k I need? What is 5 squared? It's 25 lots of 5 to the 2k, and then minus 1. Okay, last bit then. So we have an issue now though. So I've got 25 of these and then minus 1. I can't really use it because I've only got, it's only one of these minus 1. How so? What do you mean?
2k minus 1.
5 to 2k. And equals 24 plus 1.
Oh, you're saying that rearrange this and then, yeah, that would work. That would absolutely work, yes. What I prefer to do though, yeah, that would absolutely work, there's no issue with that. But what I would do we agree we need one of these, right? We've got 25, just write it as 24 of this plus 1 of this. Yeah. So 24, 5 to the 2k, plus 5 to the 2k minus 1. So now do we have the thing we need? So 24 times 5 to the 2k plus 24 hat. How are we going to show this is divisible by 24? Do we agree we can factorize out 24? 5 to the 2k plus r hat. Yeah? I put it to you that this is 24 times some number. Am I right? Yeah, it's 24 times some number. Why is this a natural number? Because we've got 5 to the power of a number, which is a number, and then we add another number, another whole number. So do you agree what you would get here is a natural number? Yeah? So it's 5 and 4 times a natural number, so proven. So you essentially need to factorize out the divisibility thing you're looking for. And we'll do another one. But these do get a bit messier, and I will might get some slightly more interesting ones over. So if you want to take a second and write that in, so if you're watching it on the video, just pause it, I guess, and write it when you need to. So I'm looking for a quite nice divisibility one, which would be great. So another thing the English exam board has is they have sequences of it, which is a bit of a nuisance. So sequences aren't really used on it. So this is quite a hard one. We won't do this one, but it'll be next. So I'll tell you what we'll do. I'm going to give you a similar one to that if you want to have a go at it.
Yeah.
Yeah, sure. I'll give you a similar one to that and then we'll look at a slightly harder one. So let me just check the camera's actually still on. Yeah. Okay, so what you have to prove is that show me that 3 to the power of 2n minus 1 is divisible by 8. For any n in the natural numbers. Show me that 3 to the power of an even power minus 1 is always divisible by 8. So again, if you're watching on the video, feel free to pause it and have a go or skip ahead. Maybe I've cropped it so that it's now, who knows. Just a context issue. When you said rearrange that one and plug that in, that would absolutely work. I just think this way makes a little sense.
How did you get 24?
So do you agree we've got 25 of this thing?
Yeah.
So I just wrote there's 24 of that thing plus 1 of it.
Oh, okay.
Yeah, so I just split. So I wanted one of them, right? So I just broke it appropriately. Josh, if you need to have with this at all, let me know. You're usually pretty good. Okay, I'm gonna wipe this off just because it's in an awkward spot, but let's go through it and I'll rewrite it. So, do we agree the statement we're proving is that 3 to the 2n minus 1 is equal to 8 times some value t, which t in the natural numbers. And I'm changing it to t because it doesn't matter what letter you use. Absolutely not, as long as you're being consistent. So, base case would be for, and then for any n in the natural numbers, this is true as well. So base case is n equals 1, so this is 3 to the power of 2 minus 1 equaling 8. Is this divisible by 8? Yes it is, so it's true. N equals k, so 3 to the 2k minus 1 equals 8. We'll say r in the natural numbers. So by my inductive hypothesis, this is true, so true by inductive hypothesis. And again, I hate writing extra stuff more than I need to, but you do need to be writing this. The marks for this are very formal. You do need to be writing it. It's a good habit to get into. Okay, so for the k plus 1 case, so this is 3 to the k plus 1 minus 1, and we're trying to prove that it's equal to 8 times s, let's say. So we're trying to prove that it's equal to 8 times some number, s, where s is in the natural numbers. Okay, so splitting this up, so do we agree that the goal is to use this statement here, essentially? So we want to get this 2k to appear. So 3 to the 2k plus 2 minus 1. So that's going to be 3 squared times 3 to the 2k minus 1, which is the same as 9 times 3 to the 2k minus 1. And I'm going to write this as 8 times 3 to the 2k plus 3 to the 2k minus 1. So now, have I created what I'm looking for? Absolutely I have. So do we agree it's 8r? And then plus 8r. So do we agree this is 8 times by 3 to the 2k plus r? And then if I call this 8 times by, I don't know, q in the natural numbers. So do we, I know we said when we were proving it was r, right? Yeah, so it's equal to some r. So hang on, the r from up here would be t, yes, t is equal to, technically. To be honest, I'm being a bit extra with this. You could literally use the same variable if you wanted to. You'd probably get away with it. I'm just being formal. So we'll be okay with that, more or less. Yeah? Good. Let's do a slightly harder one then. So, same principle applies. You've got to recreate what was there originally, or what's in your n equals k step. So, if you're on the video, you may not be able to see the board, the screen. So what I'm going to do is I'll write the question on the board once I make some space. So I'll go through it, and then we'll look at one which is similar, assuming that my stupid board goes on. Right. So, well, that should be on by now. Yeah, there you go. Right, this one's a bit harder, but again, much like when we did the slightly harder ones with matrices, you agree it's the exact same thing. You literally just got to recreate. If you want to have a go at this alongside me, feel free, but I am going to do this one just off the jump. So, for those of you watching on the video, the question is 8 to the power of n minus 2 to the power of n is divisible by 6. So specifically, the question states that 8 to the power of n minus 2 to the power of n is divisible by 6 for n. So it is divisible by 6. So I'm going to go through this one, and then I've got one that's very similar that you can have a go at. So let's get started. So base case being, so we want to prove this is equal to 6 times a, and I'm not going to write a in that. I'm fed up of writing it, you get the idea. So n equals 1, so do we agree the left hand side would be 8 to the 1, take away 2 to the 1, and do we agree that's 6? Is that divisible by 6? Yeah. Very much so. So 6, n equals k, so we have 8 to the k minus 2 to the k is equal to 6b, and this is true by inductive hypothesis. So then n equals k plus 1, so it's going to be 8 to the k plus 1 minus 2 to the k plus 1, and we need to show that this is equal to 6 times c, let's say. It's equal to 6 times c. So in this, what are the powers of 8 and 2? Okay, so do we agree? I'm just going to, right, this is 8 times 8 to the k minus 2 times 2 to the k, yeah? So do we agree I want one of these and I want minus one of these? So do we agree I'm going to write this as 7, 8 to the k plus 8 to the k, and I'm going to write this as minus 2 to the k minus 2 to the k, so I've split it as minus 1, so now we've got what I need. So this bit here is equal to what?
6k.
It's equal to 6k, good. Is there a issue here?
Should be 7 as 1.
7 and 1, and then,
Or 1 should be 1.
sorry? No, it's fine, I think we're fine. So anyway, these two here will make this, so it's going to be 7, 8 to the k, and then, what did I say it was? 6b. 6b, and then that's equal to, why is this not doing that then? Is there a problem here? Because shouldn't this be 6? Oh, I know what the problem is. Sorry, it's stupid. Right, I know what the problem is. Right. So, do you see that he takes one of these to make one of each to make 6b, yeah? How many of this can we actually make? We can make 2 of it, right?
Yeah.
So if I write this as, so my point being, the lowest one is 2, so I can write it as 2 of each, and then it's 2 times this, does that make sense? So 6, 8 to the k, plus 2, 8 to the k, and then actually I'm just going to write it as 8 to the k plus 8 to the k, that's right. See what, sorry, I'm making an absolute mess of this. We can leave this 2, it's fine. So, the idea is you just want to use up as many as you can. So 2, 8 to the k, and then minus 2, 2 to the k. So this bit here, so it's 6, 8 to the k, plus 2 times 8 to the k minus 2 to the k, right? And do we have what we need? Yeah, so it's 6 times 8 to the k, plus 2 times 6b. And do we agree this would be 6 times 8 to the k plus 12b? And what are we factoring out? Yeah, because we want to prove it's at 6. So it's 6 times by 8 to the k plus 2b. So this is equal to 6 times, the original proof was 6 times a. So yes, it is true. And then you do your usual spiel at the end, which is true for 1, true for k, true for everything. So this one's different in the sense that, do you see I actually got caught out there because I didn't use all the available ones. So do we get why I had to use this twice? Because there's enough there to make 2. So what's the HCF of 2 and 8? 2, right? So I take out, so I can make 2 of this, essentially, that will be how it is. So I'll give you this one here, you have a go at it. So similar, very similar. So I'll write it on the board for the people watching. So f of n equals 7 to the n minus 2 to the n in the natural numbers, and then it's divisible by 5 for all n. So for all n in the natural numbers, show that whatever n is, it's divisible by 5. Right, I've just done the initial bits because again they are just set up essentially. So I have another 30 seconds or so. Are we okay? This. Alright, so let's do the n plus 1, the k plus 1 case. So 7 to the k plus 1 minus 2 to the k plus 1 equals 5c. That's the objective that we're trying to solve. So this is 7 times by 7 to the k, and then minus 2 to the k times 2. Right, so what's the biggest amount that I'm pulling out? How am I splitting this? How many of these do I want? How many of this can I make? Do we agree I can make 2 at most? Yeah. So it's going to be 5, 7 to the k, plus 2, 7 to the k, minus 2 to the k, times 2. So we're lucky in a sense that this one is 2, so we don't have to take anything out, it just stays as it is. So 5 times 7 to the k, and then this bit here is 2 times 7 to the k minus 2 to the k. So by our inductive hypothesis, this is equal to 5 times b, so 5 times 7 to the k plus 5b, so this is equal to 5 times 7 to the k plus b, so this is equal to 5a. So therefore it's proven. So and then at the end you write 2 for n equals 1, n equals k, n equals k plus 1. And therefore true for all. Sorry?
Is it 5b direction 10b?
Wasn't this my original statement though? Wasn't it? Oh yeah, you're right, yes, it was to prove, yes, you're absolutely right, yes, it's to prove C. Yeah, you're right. Thank you. Okay, so this is realistically the sort of one you might get. Hang on. So if you one like this, so like this is the realistically the sort of thing you will get. So not always. Usually I haven't seen one this hard, but again, I'd rather overpay than underpay. And you have this worksheet in the Google Classroom, you can work through it. Again,